Have you ever wondered why you have to use your right hand to take a cross product? Now, I am addressing mostly students here, although maybe some of you might not know the answer. If you asked me as a postdoc, I probably wouldn't have had anything intelligent to say. In introductory physics, they just tell you, use your right hand. If you use your left hand, you get the wrong answer, right? And they're throwing so much at you that you just take it, you don't ask why, right? Now, as your physics career continues, you may learn more sophisticated ways of taking cross products. You do it with a determinant, or when you get really mature, you might start using the Levi-Civita tensor. But those ways all involve a canonical ordering of your coordinates, right? It has to go X, Y, Z. Don't mix them up, right? And that's just how it is. And so this was your first hint that there is more to the magnetic field than they're letting on in introductory physics. All right, so you join a numerical relativity group. Your advisor tells you magnetic fields are important. You have to know about magnetic fields. Why? Your advisor will tell you two things. One, magnetic fields destabilize our flows. If we have an electrically conducting fluid, weakly magnetized, and it's spinning faster on the inside than the outside, which happens very commonly in astrophysics, then you will suffer from the magnetorotational instability. This will create turbulence, right? The other thing about electromagnetic fields is they can, all on their own, carry energy. This is what you remember as the Poynting flux and angular momentum. And in particular, you can have one of these E cross B Poynting fluxes that are sticking right out of a black hole horizon. And you can extract energy from a spinning black hole this way. And this is totally allowed because nothing is falling in, no particles, no photons. Okay, so a combination of these two things means that we can transport angular momentum in our fluids, right? Which is what you need for anything to actually fall into the black hole. And we can make jets. All right, now the field of magnetohydrodynamics is in some ways younger than general relativity. A lot of the key work was done in the 40s. But it was not done with binary neutron star mergers in mind. The two problems that were driving this development were, first of all, understanding astrophysical dynamos. So things like the Earth and the Sun have large-scale magnetic fields. The Sun has a large dipole field. It reverses polarity every 11 years, and the sunspots follow this funny pattern. What's up with that? The second thing is magnetic fields are used to can be used to confine a plasma. And if you want to get more energy out of a fusion reaction than in, then you have to have the number density times the time you confine it exceed a certain threshold. And magnetic fields can potentially hold a plasma in place. Now, here's the weird thing about the magnetic field that makes it not like your ordinary vector. It is what's called a pseudo vector or an axial vector, because if you do a transformation that reverses orientation, you can think of this as active, you actually mirrored your system, or passive, you took your basis vectors and turned one the other way. The B field doesn't behave the way you would expect it to, right? So if I flip X, it's not the X component that picks up a minus sign, it's the Y and Z component. So what's going on there? And so the answer to this and my cross product question is that the magnetic field isn't really a vector. It's a two-form masquerading as a vector. What is a two-form? There's two ways to think of it. One, it's a rank 2 object, a tensor, an anti-symmetric one. And in 3 dimensions, it just so happens that when you have an anti-symmetric matrix, there are 3 independent components. So you can have one of these disguising itself as a vector, right? The other way to think about two forms are they're the things that you do an area integral over and it gives you a number. They're the integrand in an area integral. And sure enough, the B field is the thing that you integrate over a surface and you get the flux. Now, given this two form, I can maybe identify you know, say the XY component as it has to do with, we can call that the Z component, right? We can use Levi-Civita to make this identification, except you're going to pick up a square root of the determinant of the 3 metric. And indeed, when you look in numerical relativity codes, you always find this thing B tilde, which is called the densitized magnetic field. And what it really is it's the components of the 2 form, right? Okay, so same thing with like the rotation group, right? You know, there's a rotation that mixes X and Y components, right? And you can, in 3 dimensions, you can call that rotation about the Z axis. It's totally a matter of convention, whether you say that it's plus Z or minus Z, right? In 4 dimensions, right, with Lorentz transformations, right, there's a transformation that mixes like the boost in the X direction. It mixes X and T components. And it wouldn't make any sense to call it the Y or the rotation about Y or Z, right? Okay, so that's the magnetic field. It is divergenceless. So D of B, exterior derivative of B is equal to 0, which means at least locally that we can represent it as the D of a 1 form, the vector potential. Now, from introductory physics, you get the idea that when you have a no monopole field, right, that the field lines should either go off to infinity or they should make closed loops. But it turns out that's actually not true. Okay, if you do, it's true only for very symmetric systems, very simple systems. In general, what will happen with a magnetic field line is it goes around and it comes back and it's coming towards where it had started and it misses, right? And it goes off and it misses again and it keeps missing itself, right? Which, if you think about it, this is what you expect. You've got this infinitely thin, one-dimensional thing embedded in a 3-dimensional space. It would have to be, you know, you'd have to be infinitely precise to come back exactly where you started. So these field lines just go around and around, missing each other and filling up all of space. We call these chaotic magnetic field lines, not just in an evocative sense, but in a precise mathematical sense, that these field lines, they look exactly like the trajectories in phase space of a Hamiltonian system undergoing chaos. All right, so now let's put our field in with a fluid. If our fluid conducts, there will be no electric field in the fluid frame. So we can just make the Lorentz, that's the Lorentz force on a charge co-moving with the fluid equal to 0. And so that means relativistically, I just have to dot my field strength tensor into my 4 velocity. And I get a nice condition for the electric field. So the electric field is just V dot B2 form, or if you like using vectors, it's V cross B vector, right? And so the electric field is not an independent variable, right? If you got B, you've got E. Now the evolution equation. Usually I wouldn't show you derivations, but I just wanted to here because it's so beautiful. This is it. This is the derivation of the evolution for the magnetic field, right? So I just start with Faraday's law, which in form language looks like time derivative of B is equal to D times the exterior derivative of the electric field 1 form. And then I do a little trick. I added this V dot dB. I can do that because dB is equal to 0. And then I recognize, using Cartan's magic formula, that this is the Lie derivative of the B field along the velocity. So Lie derivative, what that means is that the field lines just get advected by the fluid, right? So the velocity just pushes field lines around. So the phrase that's sometimes used is the field lines are frozen in. I like to say that they are glued to fluid elements, right? So you imagine you've got this chunk of fluid, right? You know, a group of atoms that's going to move around, ions and electrons, let's say, right? And there's a field line that's going through it, right? And so later on, the fluid element is flowed over here and it's pulled the field line along with it, that same bit of the field line. You imagine it's like a rope and it's glued to that bit of fluid and it has to move with it. So it's very intuitive, right? It's an equation that actually means something. I love it when that happens. You know?
Yeah.
Something going on? Okay. All right. Okay. So the last thing I said is that field lines just flow with the fluid. All right. Now let's. Why isn't it moving?
Oh, sorry, your focus. You got to click, and then you'll be good.
Oh, okay. All right. One consequence of this is that you can wind up magnetic field lines. So by the way, the nomenclature, at least for nearly axisymmetric systems, are the two distinct components of the magnetic field are the toroidal component and the poloidal component. Toroidal just means the azimuthal component, the phi component. So a magnetic field line that for a toroidal field would be like a loop of constant latitude, right? Whereas the other components are called the poloidal field. There's a more precise definition that's more general, but for axisymmetric systems, that's what it comes down to, right? So a dipole field these are poloidal loops, right? So, or, field lines that move along longitude lines would be poloidal. So say you start off with a poloidal line and you have something like the sun, which spins, but not as a solid body like the Earth, but it spins differentially. It spins faster on the equator than near the poles, right? So you can see, imagine that field line, it's stuck, glued to the gas that it's touching at t equals 0. And so the equator pulls its part further along forward. And so you can see what happens to the field line as it gets wound up. And eventually, even though it started off poloidal, it ends up toroidal, right? You get this huge toroidal field, and this is called the omega effect. All right, now people working in the field of magnetohydrodynamics have found out that a very crucial quantity having to do with the field, key to understanding many MHD phenomena, is a thing called the helicity. And that should be only one helicity, okay? And so what this is in form language, we take the B field 2 form, wedge it into the A field 1 form, then we got a 3 form. That means that's the integrand to a volume integral. So let's volume integrate it. And you get a constant, right? If you like vectors better than forms, then take the B field, dot it into the vector potential. That gives you a scalar, integrate it over volume. Okay, so we can, this looks like this is going to be a nasty gauge dependent thing because the vector potential is in it, right? But it turns out that this is actually gauge invariant and conserved as long as we integrate over the whole system, right? So that there's no helicity, there's no flux, no boundary terms, no stuff leaving the integration region. Okay, now to do this, I need an evolution equation for the A field. And so I can just sort of take my evolution for the B field and I can uncurl it. I can basically factor out that exterior derivative. This works because Lie derivative and D commute with each other. But I'm going to pick up a gauge freedom term, right? I can throw in the the D of any scalar function I want. So the A field actually also advects up to gauge. Right? Okay, so here's the derivation. It's all right there. If we had a minute, I could walk you through this piece by piece. The trick is you integrate by parts in a couple of places, but you get 0, right? This thing is conserved, and you can sort of see from this same evolution equation how that d phi term doesn't do anything to it. Okay, so that's kind of neat. What is this thing? The helicity, it turns out it also has a meaning. It is a topological invariant. It tells us how the magnetic field lines are linked to each other, right? So things like that you see in the picture there, when field lines are not, they're linked, that's the word, linked, Okay, so measure links in field lines. And by the way, similarly, we can define helicity as associated with the velocity field and with the current, right? So if I take, to use vector language, although you can do this in form language too. If I take v, the velocity, dot it with its curl, the curl of the velocity is called the vorticity, right? Tells you angular momentum of the fluid. Then you integrate that, right? That gives you the kinetic helicity. This also is a conserved quantity for a barotropic flow. Meteorologists use this, the kinetic helicity. They use it to predict tornadoes. Okay, and how about, and the current helicity? This is sort of like you deed both of the terms that went into the magnetic helicity. It will turn out to be connected to the magnetic helicity. So take B, dot it into its curl. The curl of B is the current, if you ignore that pesky Maxwell displacement current thing. And so we've got these two other things. So all three of these will be important. Okay, now numerical relativists often, when you just want a magnetic field that's simple, you put in something like colloidal loops and you say, well, let's just let it evolve, right? So this is a zero helicity state. I mean, you can see it, right? If you just have loops, I mean, then there's no linking, right? Purely toroidal or purely colloidal fields have A dot B equals 0, no helicity. They are usually unstable, as the magnetic confinement fusion researchers learned quickly to their woe. That these are subject to kink instabilities and sausage instabilities. And then they found sort of by accident that if you add in a little bit of, a field of toroidal field, a field component along this, that tube, that it dramatically stabilizes things, right? And so there's a reason, I'll show you why we should expect that the stable magnetic fields are going to be helical ones. So let's imagine as much helicity as you could get per magnetic field. I would say the way to do that is let's make the B field and the A field be parallel to each other. That way their dot product is maximized, right? And that's the thing we'll integrate. So in 1958, Woltjer proved, the proof is simple, but I'm not going to do it, that if you look for the minimum magnetic energy for a fixed helicity, it turns out this occurs in precisely this fully helical state, when B is equal to mu times A, for this mu being a constant. The constant is basically, it's the Lagrange multiplier from when you did the minimization. Okay, so that's neat. When it's a constant, then I can D both sides, I can curl both sides, right? I get del cross B, that's J, and on the right hand, I get del cross A, that's B, right? So my fully magnetic helical field is also fully current helical. For reasons that I'll tell you in a bit, this J and B parallel to each other configuration is called force-free. And Taylor in 1974 realized that magnetic plasmas are going to just sort of naturally settle to these force-free states, right? And the reason you can imagine is that, well, I mean, you have to sort of look at it in Fourier space, but resistivity kills magnetic energy much better than it kills magnetic helicity. So helicity stays conserved even when magnetic energy doesn't. So you're sort of naturally want to, your system will want to settle to the minimum energy state that it can get to, right? Which is the minimum energy state given that helicity. So it's going to settle to a force-free state. And we've also seen similar things in astrophysics, although I don't know that the papers actually made this connection. When scientists were interested in what do we expect the magnetic field inside a neutron star to actually look like? I mean, yeah, when you merge them, usually you just throw something in, right? And it's not going to have time to evolve much before merger. But suppose you just take a neutron star and you put in all sorts of different neutron star modes and let it evolve, resistive timescales so it can settle to something. It settles to a very helical state. It's called a twisted torus, a combination of a dipole field and then but also a toroidal loops on the inside. So that's probably what we should be starting with. Okay, so these so you can also imagine you could make a magnetic wave, a wave of magnetic field that is fully helical, right? And you'd make it does this sort of corkscrew thing. And these fields, you can think of them as they're the eigenfunctions of the curl operator, right? And it's been shown that you can actually decompose any divergenceless vector field in terms of these modes. Okay, so the last bit of MHD that I haven't thrown in yet is the magnetic field does act back on the matter. And in GR, this is how you would do it. You would start off with a stress energy tensor. You know, its divergence is 0. However, it's actually made up of 2 pieces. There's stress energy for matter. There's stress energy for the electromagnetic field. Only the divergence of the total is equal to 0. The divergence of the matter, which gives you the force on the matter, is equal to minus the divergence of the T mu nu for the electromagnetic field. That works out to be the field tensor dotted into the current for velocity. And I can expand that out. There's an electric field, there's a J cross B. Usually, unless you're very relativistic, J cross B is the dominant term, right? For the Lorentz force. I can expand this thing J cross B out, again, throwing away the displacement current term, and I get 2 terms that actually make some sense. I get a magnetic pressure term that says field lines don't like to be squeezed together, and I get a magnetic tension term that says field lines don't like to be bent. And so here's the neat thing: J cross B. That's sort of the force that's acting on my fluid, right? If that's going to be 0 if J and B are parallel to each other, right? Now you understand why that's called force free, right? J cross B means, on the one hand, we are in the minimum energy state for a given helicity. It also means that there's no force on the fluid. Now, if you're in the magnetosphere of your neutron star, right, outside in the low density region where the magnetic energy dominates, right, then the fluid basically has to do whatever the field lines force it to do, right? So the field lines will move the fluid around until everything's settled. The field settles into a force-free configuration. And so you actually just solve this force-free condition and you can get the pulsar equation. Now with the last part of my time, I want to come to what's sort of one of the core issues of magnetohydrodynamic theory, which numerical relativists are only now sort of embarking on. The question of how you build up a dynamo, right? So how do we explain, for instance, the sun's magnetic field or the large scale magnetic field in an accretion disk? Okay, so the idea is that small scale fluid motions somehow wind up a large scale magnetic field. It shouldn't be obvious to you that this should work at all, right? So for instance, we know with our accretion disk simulations that at least, at the early times, what happens is you have, the magnetorotational instability starts growing. This is a linear instability, and for a small magnetic field, it grows on small scales, right? It doesn't make a large scale magnetic field. So you need more than this initial MRI exponential growth to explain a large scale field. And yet it happens, right? We can see it with the sun, it happens. Okay, and it happens with accretion disks too. So here's a paper I happened to be reading a few days ago, and I stole an image from it. So what you're looking at here is the average toroidal field as a function of time. Time on the horizontal axis, and I think distance from the equator on the vertical axis. And you get, it actually flips right over time. It looks like these sunspot butterfly diagrams. So, there is in addition to this, small scale turbulent field, there is this overall field that's going on in disks and the sun and the galaxy and the Earth. Okay, so how are we going to do this? Okay, so first thought, stars, disks, they're all pretty much axisymmetric, as are, the large scale fields that we want to understand, both the colloidal bit and the dipole bit. So this should be an axisymmetric model. Okay, so we'll evolve it in 2D. Everything's a function of r and theta. Nothing is a function of phi. That will simplify our lives and our CPU usage so much. The problem proved by Cowling in 1933 is that you will definitely fail. If you just take the MHD equations and evolve them in axisymmetry, you can prove it's impossible to make a dynamo. And indeed, one can even see in 2D MHD simulations, right? So the harm simulations going back decades. Originally, they were done in 2D, and the magnetic field amplifies beautifully, to equipartition. It saturates, and then it fairly quickly dies out, right? Something that doesn't happen in high-resolution 3D simulations. So this is a problem. It seems like we at least need 3D, and you wonder, how is it that these roughly axisymmetric systems are doing it? And the basic idea to the solution was discovered by, or thought up by Parker in 1955, and I believe in the context of the Earth's dynamo. And he thought, well, okay, maybe it's sufficient just to have non-axisymmetry on small scales, right? You have this churning, from convection or whatever on small scales, even though, it averages to 0 on the large scale. And so the average large scale velocity in magnetic fields, they'll still be axisymmetric. However, the evolution equations, right? The Euler equation for the fluid and the induction equation, the frozen equation for the magnetic field, they're going to look different, right? There's going to be, when you average out the small scale stuff, the average of these fluctuations is actually not 0. It's going to give you, for the evolution of the velocity, there might be some mean force, that will affect the axisymmetric evolution. For the magnetic field, there might be some mean electromotive force that drives the magnetic field. So at this point, I'll just pause and say I've been sloppy talking about average and small scale, or average and fluctuations, deliberately, because really we have to think a little bit about what we mean by our small scale stuff and our large scale stuff. There are two things you might mean. One, you might mean, but small scale might just mean non-axisymmetric, right? I have, so it means, so the large scale means m equals 0, and small scale just means any non-axisymmetry, right? That was actually what was done first. The other thing you might mean is really small scales, right? I'm say I do a Fourier transform of my flow, and I just throw away all the high K number modes, right? That might mean, the low K number modes might mean the average, the high K number modes might mean the fluctuations. It turns out that the math is extremely similar, no matter what you mean by it. So the idea is we're going to take everything, the velocity, the magnetic field, and the other interesting variables, although that's usually it, and say each one is made of its mean component and then its fluctuations. And then we take our evolution equations and then we do a mean operation on them. So in these slides, I'll say by mean, I mean this bar over it, right? It means average out. So, if we're talking axisymmetry, it means, average over phi. If we're talking about, large scales, then, you'll convolve with some smoothing function, or you'll just, you'll do the Fourier transform and throw away the high K modes. Okay, so here's the thing. So here's where the dynamo terms, the new dynamics comes in. We take our evolution equation for the magnetic field, which I've written here in vector form, right? So ignore those overbars for the moment. The magnetic field evolution says partial TB equals curl of B cross B. Now I average this over whatever. And so I get time derivative of the average of B, and average, we'll say, commutes with curl. So it's equal to the average of V cross B. And so here's the thing, average of V cross B is not necessarily the same thing as average of V cross average of B, right? If there's some correlations, right, it might not be. So let's say that we take, yeah, so let's say the average of this EMF of B cross B is equal to, on the one hand, there's the cross product of the averages, and then there's some leftover, right? I'll just call it delta E. That's just whatever the difference is between these two, the average of the product and the product of the averages. And you can work it out if, I replace V and B with, so V is V average plus delta V, B is B average plus delta B, right? For this residual, I get what it is it's the delta V cross delta B average of that. So it's my small scale EMF averaged into the large scale. Okay, now if we want to have a model that where we only know the large scale stuff, the small scale stuff is subgrid. It's stuff that's we haven't kept track of. We would like to express this delta E in terms of things that we have. We want to express it in terms of the average magnetic field, the average velocity or something. And so what you do is you just you guess a closure model. You just say, okay, well, I'll take all of the averaged quantities I have and say that the thing I don't know is just some combination of every term I can think of, right? This is how phenomenology works, right? And then I'll put some unknown coefficients out in front and guess what they are, right? Or try to find some, or I'll calibrate it somehow to experiment or to numerical data, right? So I'll say, well, what have I got that's a vector? I know I've got the magnetic field, right? I got the average magnetic field. So maybe there's a component to this residual EMF that's proportional to the average magnetic field, right? And I'll put a proportionality constant in front of it. In general, it should be a tensor, right? Alpha ij times B average j. A lot of times you'll see that studies will just assume that the tensor is isotropic and make it a scalar, right? That's probably a very questionable assumption for something like an accretion disk where there's this very strong azimuthal structure, right? So, but let's say that there is such a term. I'm not going to have a whole lot of time. So let's leave out that next term, the curl term, right? Because that just ends up acting like a resistivity. Okay, what's really interesting is that first term, the alpha term, right? It's always called alpha, right? Unfortunately, the lapse is always called alpha, and the artificial viscosity are also always called alpha. So I put a little d there, the dynamo alpha, right? And so why is this interesting? This is interesting because it's like a source term for magnetic field, right? If this term is there, then it lets you make toroidal field from poloidal field. It lets you make poloidal field from toroidal field, right? It lets one type of field be the source for the other type. So in principle, you could even make a dynamo with no rotation at all, right? That's called an alpha squared dynamo, where the toroidal field and the poloidal field just feed on each other through this alpha effect. Or, I mean, if you've got rotation, like in a disk or a rotating star, like the stuff we do, you actually only need the alpha effect to make yourself some poloidal field from toroidal field, right? Toroidal field you can wind up through the omega effect. Okay, so that's the idea, right? Is if these residual terms do their job, then we can make large scale fields, right? Small scale churning can make large scale fields. Okay, so now we really would like to not just have this all important alpha D be put in by hand, and you say, gosh, I hope it exists. We'd like to know what causes there to be a non-zero alpha D, and you can do a nice little calculation. I won't do it here. I'm not even going to show it this time. I'm just going to give you the answer. So here's what you would do. You would say, okay, I remember there's this equation for delta E, right? Here we are. So there's delta V cross delta B. I'm going to work out the time derivative, the evolution equation for this residual, right? What causes, maybe I don't know what it is, but what would cause delta E to increase? What would cause it to grow, right? Well, so I do a time derivative, and the time derivative is just, there's going to be two terms, right? Product rule. I need to know time derivative of B, right? So I'm going to substitute in the Euler equation. I need to know time derivative of B, delta B, right? So I'll substitute in the induction equation. And so you do that, and you do the math, you turn the crank, and what you end up with is, it's very cute. On the one, you got two terms. The first one was, so delta omega, if you forgot, was the curl of V, the vorticity, right? So delta of omega dot delta of V. Remember, omega dot V is the integrand for kinetic helicity, right? So it's the small scale kinetic helicity minus delta J dot delta B. This one, hopefully you remember, that's the small scale current helicity. So that's the answer, right? It turns out that if you want to make a dynamo, what you need, in your small scale flows, you need kinetic helicity or current helicity. That's what'll give you an alpha. And if you've got an alpha, then this small scale churning won't just average out to 0. It'll average out to a source term for the large scale field, right? Structure will flow from small scale to large scale. All right, so I'm out of time. So I'll just say but this is it. This was all this. I would say there. So over the last several decades, in dynamo theory, there's been there's been a great deal of progress in understanding, not only how dynamos start, but how they saturate. What level the large scale field gets to when the growth stops, and helicity is really sort of the key to the whole thing, right? So we need helicity to make there be alpha effect. It turns out that you also have helicity as the thing that makes the alpha go away when the magnetic field gets big enough. Basically, it seems that as the field grows, this thing starts growing and it cancels out this thing, right? And if you want to have a bigger field, one of the ways you can make this happen is you can suck helicity out of the current helicity out of the small scales, so that it takes longer for this to happen and you saturate at larger values. But again, helicity seems to be the conceptual key to understanding all this stuff. So, thank you. I don't know. I want you to have some background outside of just what we do. So you can take these ideas and use them if they are useful.
Yeah. All right. So let's see. Do we have any questions in chat? First off.
So,
or actually here, please.
So if the small scale is flowing into the large scale, what does that mean for the resolution of simulations you want to do? I mean, do you have to
Yeah, it's hard, right? Dynamo theory. This is what makes it harder than turbulence theory.
Maybe a good idea to repeat the questions for the sake of those who are online.
Oh yes.
Oh, I could use my mic.
No, that'll make echoes, I think. Yeah. So the question is, given the transfer of energies from smaller scales to larger scales, what impact does that have on our understanding of what sort of resolution requirements we may have in numerical simulations?
Right. And yeah, and that's a good question, right? Because it is, this is what makes dynamo theory harder than turbulence theory, you could say, right? In turbulence, the cascade is all the smaller scales, right? Where the energy just goes away into heat. Whereas in in the dynamo case, it actually goes the opposite way, right? And you have both energy and helicity. It turns out to be, one of the key things is, helicity of one sign goes to large scales, and helicity of the opposite sign goes to small scales. And so you need to. I think it shows that you basically. You can't have a dynamo model, without having either, some subgrid treatment, right, that handles, what's supposed to be happening at smaller scales, or you go all the way to the resistive scale.
Could you maybe do some sample small scale simulations to get some kind of average effect, and then put them into the larger scale simulation?
possibly, I mean, if you had the smallest scale,
Yeah.
Right,
I'm
that's-
just trying to think what
yeah.
you need to do.
so even we often in numerical relativity we treat the MRI fastest growing wavelength as the small scale, but that's actually optimistic, right? I mean, that's where you're injecting energy, and actually there'll be a turbulent cascade to smaller scales than that. You know? And so, I mean, initially, the magnetic field will probably just be on these, in these smaller scales, you'll have what's called a kinetic dynamo, where the magnetic field is small and just gets wound up by small scale eddies, right? But I mean, eventually, you'll get to a high enough level that you can have feedback even there. The small scale dynamo will quench.
Yeah, Roland.
So if we have time. So basically from what you hear, you would say that we probably have no real chance of actually solving this thing down to the actual scales where this becomes relevant in any foreseeable computer. So you need a subscale model. Do you have a preference what you might want to use there?
Let's see. Well,
Can you repeat the question about what is the
Okay. Yes.
So you actually tracked everything that you said, so I'm assuming they partially heard at least.
Yeah, it was loud. No, I could hear it pretty well from here.
All right. Yeah. So the question is, okay, if we need a subgrid model, what do we use? All right. Well, one thing you can do is you can start with things like this. So what the place where this expression came from, I mean, it may look kind of arbitrary, but what it's based on was, we think it's got to be proportional to the magnetic field, and it can be proportional to its derivatives. And so, maybe we will, if there's some sort of separation of scale, right, then we can do an expansion in terms of derivatives of the B field, and we can drop it after the first derivative, right? Now, it seems to me like one might consider also having terms proportional to the velocity, right? I mean, you would want to have some, B scalar on the outside. And as for these unknown coefficients in front, they're constrained in several ways, right? I mean, first of all, they're constrained by symmetries, right? So they must be. Do I want to see? I mean, I'm going to say generally covariant, but your problem may have preferred directions, right? So, for instance, in an accretion disk, I mean, if you're azimuthally averaging, it seems to me that the phi unit vector can certainly come into your expressions, right? That would be an entirely natural thing to happen. Also, there are parity issues, right? So, for instance, this alpha d thing is, you can't just throw in a scalar. You can't just say, let's say it's proportional to rho. It's rho times 0.1, because because E is a polar vector and B is an axial vector, right? It's one of these things I had to use Levi-Civita to take my two form and make it into a vector. So they behave oppositely under orientation reversals. So what I need to have here, what I need for alpha to be is, I need it to be some sort of a pseudo scalar, right? So I could do something like, if I take an axial and a polar vector and dot them into each other, So there are constraints, right? To what types of terms you can throw in here, thankfully.